just as various quantities have SI units, the unit of amount of substance is mole. 1 mole of any substance is the amount of that substance that contains as many elementary particles as there are in exactly 12 grams of carbon-12. These elementary particles could be atoms, molecules, or ions. Thanks to a scientist named Amadeo Avogadro, we now know that if we should take 12 grams of carbon-12 and we should measure weight, we will discover that it contains exactly 6.02 times 10 raised to the power 23 particles. This means that according to our definition, 1 mole of a substance is the amount of that substance that contains 6.02 times 10 raised to the power 23 entities or particles. In the same manner, the molar mass of a substance becomes the mass of 1 mole of that substance. In order to understand, we want to compare the mole to a dozen. Just the way 1 dozen of eggs contains 12 eggs, because the word dozen means 12, I would like you to take 1 mole of any substance to be equal to 6.02 times 10 raised to the power 23 particles of that substance, because the mole is equivalent to 6.02 times 10 raised to the power 23. So do not think of the mole as something complex. Think of the mole as a number. Mole equals 6.02 times 10 raised to the power 23, just as a dozen is equal to 12. To get the number of moles in a quantity of a substance, we simply divide the mass of the substance by its molar mass. That is, number of moles N is equal to reacting mass over molar mass, or N is equal to small letter m over big letter M, where N equals number of moles, small letter m equals reacting mass, and big letter M equals molar mass. Let's take an example. Take this question down. If we have 40 grams of H2SO4 or sulfuric acid, and we want to know the number of moles of H2SO4 in a sample, all we have to do is to simply divide the given mass, which in this case is 40 grams, by the molar mass of H2SO4, which is 98 grams. Therefore, the number of moles becomes N is equal to reacting mass 40 over molar mass 98. Dividing mathematically, this will give us 0.408 mole. It is quite easy, isn't it? Please, I would like you to pause at this moment to assimilate the above details. Sadly, many students despise chemistry because of the calculations in chemistry. However, my friends, I have taken my time to explain the mole concept, and I will further explain it to ease you of any stress that you may feel or you may encounter in calculations in chemistry. So right about now, I am going to teach you stoichiometry. Have you heard of that term before? Stoichiometry is an aspect of chemistry that students find so difficult. But in the next few minutes, I will present to you stoichiometry in the easiest format possible. So what is stoichiometry? Stoichiometry simply deals with the determination of amounts or quantities of substances in chemical reactions. Since the unit of amount is mole, a good understanding of the mole concept will prove to be helpful. In our definition, we also said that stoichiometry deals with the determination of amount or quantities of substances. These quantities may be number, may be mass, or may be volume. So, we are going to see how the mole and quantities interplay in chemical reactions. The mole can be expressed as a number as a mass and as a volume. Let's take the mole as a number. As a number, 1 mole of any substance is equal to 6.02 times 10 raised to power 23 entities of that substance. It means that 1 mole of sodium atom contains 6.02 times 10 raised to power 23 sodium atoms. In like manner, 1 mole of the oxygen molecule is equivalent to 6.02 times 10 raised to power 23 oxygen molecules. So in this manner, we can represent the mole as a number where mole at any time being spoken of can be represented with the number 6.02 times 10 raised to power 23. The mole can also be represented as a mass. In this case, 1 mole of any substance, be it an atom, a molecule, or a compound, is equivalent to the atomic mass if it is an atom, the molecular mass if it is a molecule, or the formula weight if the substance in question is a compound. It means that according to our periodic table, where we have sodium having an atomic mass of 23, 1 mole of sodium atom is equivalent to 23 grams. In the same way, since the molecular mass of oxygen O2 is 32 grams, 1 mole of oxygen molecule is equivalent to 32 grams. So you can see that we can convert 1 mole of any substance to its mass simply by calculating its atomic, its molecular, or its formula weight. So if we have H2SO4, can you probably guess the equivalent mass of 1 mole of H2SO4? Remember that H2SO4 is a compound that contains hydrogen, sulfur, and oxygen. H2SO4 means we have two atoms of hydrogen, each having a mass of 1. We have 1 plus 1 equals 2 grams. Sulfur has an atomic mass of 32, so the 2 grams of hydrogen plus 32 grams of sulfur equals 34 grams. And then oxygen has an atomic mass of 16, but in H2SO4 we have 4 atoms of oxygen. That becomes 16 times 4, which is 64. Adding the mass of oxygen, the mass of hydrogen and sulfur, we have 34 plus 64, and that is 98 grams. So it means that 1 mole of H2SO4 is equivalent to 98 grams. As a volume, 1 mole of any gas, as this only applies to gases, occupies a volume of 22.4 dm cube. So it means if I look carefully at any chemical reaction and I see that 1 mole of any substance, be it an atom or a compound, is given, as far as that atom or compound is a gas, I will know that at standard temperature and pressure, 1 mole of that gas occupies a volume of 22.4 dm cube. How would I know it is 1 mole? It will have no coefficient, and then I will know it is just a mole of that substance. We have seen how the mole can be converted to a number, can be converted to a mass, and can be converted to a volume. Let us apply this newfound knowledge by using analytical questions. Let's take the first question. 50 grams of carbon monoxide is burnt according to the equation below to produce carbon dioxide. The equation is 2CO plus O2 gives us 2CO2. Calculate the volume of oxygen that is used up at STP. In questions like this, my friends, I am about to give you 3 steps that can solve any stoichiometry question that you may encounter in your exam. What are these 3 steps? They are: step 1, isolate; step 2, convert; and step 3, ask. So let us apply these steps. Step 1, isolate. Now looking at the question, you will notice that carbon monoxide was talked about in the sense that we are given a figure for carbon monoxide, the mass of carbon monoxide. And also we are asked about the volume of oxygen that is used up at STP. So isolating, We are going to bring out the only two things that matter in the question, and they are what? Carbon monoxide and what? Oxygen. So you have the equation on the board. Look at the equation. I'm going to isolate or bring out carbon monoxide and oxygen such that we have 2CO plus O2. I have isolated. Step 2, convert. Now in the equation, we have 2 moles of carbon monoxide being combusted by 1 mole of oxygen. To convert, I will look at the question and notice that in the question, the mass and not the mole of carbon monoxide was given, and I was asked for the volume of oxygen. So I am going to convert the 2 moles of carbon monoxide I have to mass. So how would I do that? I have to calculate that 1 mole of carbon has a mass of 12 grams plus the 16 grams of an oxygen atom, and that will give me 28 grams. So carbon monoxide on its own has a molecular mass of 28 grams, but I have 2 moles of carbon monoxide. So 2 times 28 gives me 56 grams. Hence, I have 56 grams of carbon monoxide in the question. Now let's convert the oxygen to volume. Remember we said that 1 mole of any gas at STP occupies a volume of 22.4 dm3. In the question, we have just 1 mole of oxygen, so the volume of oxygen here is 22.4 dm3. So we can see that converting, we have 56 grams of carbon monoxide is reacting with 22.4 dm3 of oxygen. Now the next and final step is to ask. So we would ask our question in this manner. If according to the balanced chemical equation, 56 grams of carbon monoxide is supposed to react to 22.4 dm3 of oxygen, what volume of oxygen will be needed to react to the 50 grams of carbon monoxide that was given in the question above? Thus, we have carbon monoxide plus oxygen, 56 grams to react to 22.4 dm3. We were given 50 grams. So if 50 grams is reacted instead of 56 grams, what will be the volume of oxygen that 50 grams will react with? Let's cross multiply. Cross multiplying, we have 56 grams times the x, or the unknown volume of oxygen, will be equal to 22.4 times 50 grams. 56x is equal to 1120. X equals 1120 over 56, and this will give us 20 dm cube. So it means that while 56 grams of carbon monoxide will react to 22.4 dm cube, the volume of oxygen required to burn 50 grams of carbon monoxide is 20 dm cube. Now let us try and see if we can solve for the mass of CO2 produced. So I shall be taking this as the second part of the question, the mass of CO2 produced. So the question still goes like this. If 50 grams of CO is burnt according to the equation below to produce carbon dioxide, calculate the mass of CO2 produced. So let's apply our steps. Let us isolate. To isolate, excuse me, to isolate now, you will notice that the two important things in the question become what they gave us, carbon monoxide, the mass of carbon monoxide, and what we are now looking for, the mass of CO2 produced. So I'm going to bring out carbon monoxide and carbon dioxide from the equation. So bringing it out, I have 2CO will give me 2CO2. I have isolated. Step 2, convert. What was said about carbon monoxide? Mass, not to 50 grams. And now they are asking us for the mass of carbon dioxide. So it means that in both cases, we have to convert the moles of the two substituents in the reaction into their various masses. We have calculated earlier that 2 moles of carbon monoxide is equivalent to 56 grams. Let us calculate for 2 moles of carbon dioxide. To make it easy, carbon dioxide on its own has a mass of carbon 12 plus oxygen molecule 16 times 2, 32. So 12 plus 32 equals 44 grams. So 1 mole of carbon dioxide has a mass of 44 grams. But in the question, as you can see on the board, we have 2 moles of carbon dioxide. So 2 moles of carbon dioxide will be equal to 2 times 44 grams, and that will give us what? 88 grams. So let us now ask, if normally 56 grams of carbon monoxide should react with oxygen to give us 88 grams of carbon dioxide, what will be the mass of carbon dioxide produced if, according to the question, we are given 50 grams of carbon monoxide? Calculating mathematically, cross multiply, we have 56x equals 50 times 88. Solving mathematically, we would have that x, which is the unknown mass of carbon dioxide produced, is equal to 78.75 grams. I'm sure you've been following through. Of course, I'm also sure that you are wowed because these 3 steps are so easy, so quick, and they always give the correct answer. Let's take another example. So, example 2. 100 dm cube each of methane and oxygen are completely exploded together. They react to yield carbon dioxide and steam according to the equation below. Methane plus oxygen gives you CO2 plus water. Balancing the chemical reaction, 1 mole of methane will react with 2 moles of oxygen to give carbon dioxide and 2 moles of water or steam. Calculate 1. The maximum volumes of each of carbon dioxide and water or steam that can be produced from the reaction. 2. The mass of CO2 obtained. And 3. The actual amount of steam obtained. Let's be given some standard figures now. So here we have the atomic mass of carbon is equal to 2, that of hydrogen is equal to 1, that of oxygen is equal to 16, and the molar volume of any gas at STP is equal to 22.4 dm cube. Are you eager to solve and to demystify this question? Solution. First, we were asked to calculate the maximum volume each of CO2 and steam produced. Now this question, actually we have to think something about this question. Observing the question on your screen, you will notice that we were given equal volumes or amounts of the reactant. They gave us 100 dm cube each of both methane and oxygen. In this type of question, we should first and foremost determine which of the reactants is in excess. To do this, we have to compare their stoichiometric ratios. Now looking at the chemical equation, you will notice that 1 mole of methane reacts with 2 moles of oxygen. Thus, the ratio of methane to oxygen, as you can see in the chemical equation, is 1:2. Thus, if 100 dm cube of oxygen is used, it means that this 100 dm cube of oxygen must have consumed only 50 dm cube of methane due to their stoichiometric ratio 2:1. And that means that the other 50 dm cube of methane that did not partake in the reaction is referred to as excess gas. So, the volume of oxygen that will be used up will determine whether the reaction will come to a halt or not, despite the excess of methane present. Let me explain that again. We were given equal volumes of oxygen and methane, 100 dm cube each. According to the ratio in our equation, we can see that the ratio of oxygen to methane is 2:1. Following that ratio, it means that 50 dm cube of methane will only react with 100 dm cube of oxygen, or 100 dm cube of oxygen will exhaust only 50 dm cube of methane. But what about the excess 50 dm cube of methane? This will not partake in a reaction. So, because the entire volume of oxygen has been used up in consuming only 50 dm cube of methane, the reaction will come to a halt, or the reaction will stop. This means that oxygen is what determines if the reaction will continue or not. As a result, oxygen is called the limiting reagent or the limiting reactant. Now, I want to help you. I'll give you an illustration to explain what I mean by limiting reagent. Assume that an award is composed of two spoons and a cup. Or let's say that your parents awarded you the responsibility to share gift sets for children in particular school. Each gift set contains two spoons and a cup. If you are given 70 spoons and 30 cups and are required to distribute these gift sets to children at the school, you find out that upon giving the 30th cup or the last cup, you'll be given exactly 60 spoons. This leaves you with 10 excess spoons since you were given 70 spoons. And it indicates that the cups were insufficient. Now, you cannot continue giving out gift sets, not just because of the spoons being in excess, but also because of the cups being insufficient. This is the insufficient species, in this case the cups, and because the cups are exhausted, this will now stop your sharing of gift sets. So it means that it is the cups that determine the limit or how far the process of sharing the gift set goes. This is the same as in reactions. The cup of course becomes the limiting reagent. It is important to realize that when we say a reactant determines the limits of a reaction, it also means that this reactant is what will determine the quantities of the products that will be formed. Thus, in our calculations, we shall use oxygen as a standard for the determination of product amount since oxygen is the limiting reactant. I think we are ready to solve the questions above. Now take a look at the chemical equation again. Two moles of oxygen react to give carbon monoxide and carbon dioxide rather and steam. I have decided to take out methane because we are dealing with just the limiting reagent, oxygen. 2 moles of oxygen will give 1 mole of carbon dioxide and 1 mole of steam. Representing the mole as volume, I can equally say that 2 volumes of oxygen will react to give me 1 volume of carbon dioxide and 2 volumes of water. Since the volume of oxygen given in question is 100 dm cube, we shall take this as 2 volumes. Thus, 2 volumes of oxygen reacting to give 1 volume of carbon dioxide and 2 volumes of water will be equivalent to 100 dm cube reacting to give 50 dm cube and 100 dm cube of water. Therefore, the volume of carbon dioxide and water or steam that is produced are 50 dm cube and 100 dm cube respectively. It's that easy. Now what if we are asked to calculate the total volume of the gas in the reaction vessel at the end of the reaction? This can be calculated by adding the volume of the product. The volume of the product in this case becomes 100 dm cube plus 50 dm cube, and we have 150 dm cube. But remember that we said earlier that out of the 100 dm cube of methane provided, only 50 dm cube reacted, 50 dm cube did not react. So this 50 dm cube of unreacted methane will still be in the reaction vessel. So we are going to add this to the amount of product formed, and we have 150 plus 50 dm cube of methane, thus giving us 200 dm cube of gases that remains in the reaction vessel at the end of the reaction. Let us calculate the third or the second in the question, the mass of CO2 obtained. The task here is just to convert the volume of CO2 produced to a mass. My friends, recall that 1 mole of CO2 is equivalent to 22.4 dm cube of CO2. Since CO2 is a gas, and is also equivalent to the molecular mass or the formula weight of CO2, which is 44 grams. Therefore, if 22.4 dm cube of CO2 is equivalent to 44 grams of CO2, 50 dm cube of CO2 will be equivalent to x grams of CO2. Cross multiplying, we have that x grams of CO2 is equal to 50 times 44 divided by 22.4, and this will give us 98.2 grams of CO2. So 98.2 grams of CO2 is the mass obtained at the end of the reaction. Lastly, we were asked to calculate the actual amount of steam obtained. In stoichiometry, the amount of substance should be represented in mole, since the unit of amount is mole. Thus, all we have to do is to convert the volume of steam obtained into a certain number of moles as follows. 1 mole of steam is equal to 22.4 dm cube of steam. X mole of steam will be equal to 100 dm cube of steam, as we calculated earlier. Thus, the amount of steam that occupies a volume of 100 dm cube of steam will be equal to 100 times 1 over 22.4, and this will give us 4.46 moles. So we can see that a 100 dm cube sample of steam actually contains 4.46 moles of steam. Please, I beckon on you to pause the video now to review these calculations over and over again, probably with a rough sheet. Check if you can solve them yourself before you proceed.